Thank you very much for the introduction, and also thank you very much for hosting me as a visiting professor at the Yukawa Institute. I'm enjoying very much. Had a lot of interesting discussions, and will be still around until beginning of July. Yeah. Okay, so in today's talk, I want to give you a little bit of a taste of the research we have been doing in Stuttgart with my research team, and I want to present two strategies to find topological materials. But before I start, I would like to thank my group members and collaborators. So the work I'm going to present today has been done by my PhD students, Moritz Hirschmann, who has just moved to Riken a week ago, where he's doing a postdoc. Also with Pietro Bonetti, who did a lot of this functional normalization group I'm going to talk about in the second part of my talk. Kirill Alpin, who is going to finish this year, and also Niklas Heinsdorf, who is a third-year PhD student. So actually, Moritz and Niklas, they will be visiting Yukawa Institute next week, and you're also welcome to talk to them if you want to. And then I would also like to acknowledge collaborations with Emalia Chakraborty. He was visiting me last summer, who was working on these Rashba-Hubbard systems, and also Xianxin Wu, who was also involved in this work on topological superconductors. Okay, so the broad theme of my talk today is topological materials. So what is a topological material and why is it interesting? So very roughly speaking, a topological material is a material which exhibits certain properties, unusual properties that are unaffected by deformations. So this can be, for example, surface states, which are robust to deformation. So in particular, they can be robust to impurities. So one example is shown here, where we have a churn insulator, which has a chiral surface state, which can carry current around the edge of the sample. And this surface state is robust against deformations of the system. So we can deform the shape of the system, we can stretch it, we can compress it, or we can add even disorder to it, and the surface state will not disappear. So and why is this? This is because it has a topological origin. It comes it's protected by a so-called topological invariant, which somehow is a mathematical tool to characterize this robustness against deformations. And so this property of this robustness of these surface states and also certain bulk properties of topological materials then has led to the idea to use these systems for potential applications, right? So this is something very useful if you want to make an electronic device. You want to have something that is robust, you know, even if this is in a real world application, you might have some perturbations from the environment. So you want to have certain effects which are very robust. So this has led to a lot of ideas to use these materials for applications. For example, there are ideas to use this for high-speed or ultra-low power electronics. And so this could become relevant in the future because right now more and more energy is used for computing, for running these servers and these clouds. It's around 10% of the world's electricity, and this is doubling every decade. So eventually, we're going to run into some problem when we use too much energy for these computing applications, and this could be maybe one way to solve this by trying to find or develop new devices based on these topological materials. Another potential use of these materials are the superconductors. So kind of these properties not only apply to insulating band structures, but they can also be applied to superconductors. And so there, these topological properties can protect certain aspects of the superconductors. They can protect entanglement. They can in particular also protect surface states, which come in the form of Majorana modes. And we have just heard a talk from Jinkai early this week on these Majorana modes and how they could be applied to make a qubit. Okay, so maybe a second motivation to study these topological materials is that they have you have an interesting correspondence between condensed matter aspects and you know, concepts from high energy physics and from mathematics. For example, there is interesting connection between these materials, the classification of these materials and homotopy theory, or K-theory and index theorems. So this is basically has to do with the fact that when we classify these materials, we define so-called equivalence classes. For example, here is shown again the band structure of a Chern insulator. And so this classification is kind of based on the concept of equivalence classes. So we say if we have like two band structure which can be deformed into each other. So again, this concept of deformation that should not destroy the property of the material, then they belong to the same equivalence class. And this also applies to the surface state. So one can define these kind of equivalence classes. They can be viewed as a group, and then they can be related to these K groups from K theory, or they can be related also to homotopy theory. So the simplest example where this works would be the SSH chain, which is a 1D system defined like this. So in 1D, the Brillouin zone is just a circle, and Hamiltonian can also be viewed as a circle defined by these two vectors, D1 and D2. And then the Hamiltonian just defines a map from the circle S1 to the circle S1. And then we just know from the first homotopy group that this classification is C. So they are kind of a very rich correspondence between these material aspects and complicated mathematical concepts. Okay, so now over the last few years, there have been a lot of studies to classify these types of materials using these topological concepts, and numerous articles have appeared where complete, or at least that's what they claim, complete catalogs of topological materials have been enumerated. However, there is still kind of missing, what is still missing is to find kind of a key useful material that could be employed for these applications. You know, for example, we're still looking for an ideal superconductor which houses these Majorana modes, and we are still looking for an ideal material which would realize a Chern insulator, which would have edge states with very low dissipation. And so this, with this, I kind of want to motivate my talk and present in my talk two new strategies to find topological materials, and these strategies will, at least to some extent, overcome some of the difficulties that we have been facing so far. So this leads me to the outline of my talk. So basically I have two parts. The first part deals with normal state materials, so with metals which have Fermi surfaces. And I want to use here the concept of global band topology and symmetry constraints to derive a strategy to find metals with Fermi surfaces that have so-called topological nodal planes that lead to interesting response functions. And then in the second talk, I would be talking about superconductors. So as I said, these topological concepts can also be applied to superconductors. And I want to introduce a new numerical method, which is based on a functional randomization group combined with a real space mean field theory, which will allow us to study model systems close to Van Hove singularities, where we can expect superconducting states with large transition temperatures. And with this method, we can also include the effects of disorder. So this is something that has always kind of hampered the field, that you have interactions and disorder at the same time, and this makes it difficult to analyze the data and make reliable predictions. Okay, so we'll start off with this first talk, the first part about this material with topological nodal planes. And so basically here I have two motivations. So maybe some of you have heard about these topological semimetals already. For example, there are these Weyl semimetals where you have a point crossing. So you have two bands crossing at a single point in the Brillouin zone that forms a Weyl point, which is protected by a Chern number. So this is an example of a topological semimetal, but then this special crossing protected by topology can also have higher dimensions, so it can be also one-dimensional. So in so-called nodal line semimetals, one has two parabolic bands which overlap with each other, forming a ring where you have a twofold degeneracy. So these types of semimetals have been studied a lot. Now the question is, can we have such a degeneracy in the band, which carries a non-zero topology, can we have that also in 2 dimensions? So can we have 2 bands overlapping on a 2-dimensional submanifold of the Brillouin zone, and such that they carry a finite topological charge? And the second motivation has to do with some of these challenges that we usually have in the field, right? So if we look at these Weyl semimetals or these nodal line semimetals, usually the problem is that these band crossings, these Weyl points, are not at the Fermi level, because by symmetry they do not need to be at the Fermi level. Someone needs to have some fine-tuning, or for the material one needs to have the right doping to put this this Weyl point at the Fermi level, such that it dominates the transport properties which would be important for an application. Another problem is that often one has these oppositely charged Weyl points very close together in the Brillouin zone. So then the effects, these topological effects that one would like to see in the transport, would be washed out by disorder. And moreover, they will be rather small, because these topological effects, like the Harmonic Hall effect, scale with the distance of these oppositely charged Weyl points in the Brillouin zone. So we would like to have oppositely charged objects that are far away in the Brillouin zone. The third challenge has to do with this charge of these Weyl points. So these Weyl points, as I said, are protected by a Chern number. So this is can be viewed as a topological charge, which takes an integer value. And so typically this is can only take up to number 5, because of symmetry constraint, larger charges are not possible in these Weyl semimetals. But we will see that for these nodal planes, you can overcome this challenge. And finally, we would like to have a good handle to somehow control the topology of these band crossings. Yeah. And we will see that these nodal planes hopefully will at least partially help us to overcome these challenges. Okay, so to find material with the topological nodal planes, I'm going to use these concepts of a local and global constraints, so concepts of global band topology. And I'm going to use the following 3 fundamental theorems that we have explained in this recent arXiv article. So these are constraints that tell you something about these chiral band crossings in general. And so we have a local constraint. So this relates this Chern number that protects the crossing, for example, a Weyl point. And it relates this Chern number to the jump in the eigenvalue. So for example, if we have a rotation symmetry, we can label the states in terms of the eigenvalue of this rotation symmetry. So here lambda plus and lambda minus. And these eigenvalues, they have a phase usually. And what happens is at this crossing point, you have a phase difference between this lambda plus and lambda minus. So this is this delta phi. And there's a general condition which relates this Chern number to this jump in the phase. So this is the first global constraint. And so here this prefactor has to do with the order of the symmetry. So if we have a 2-fold symmetry, this n will be 2. And then this phase jump would be typically here maybe pi. So then you have 2 pi over 2 pi. And the Chern number would have to be plus or minus 1, dictated by the symmetry. Then the next fundamental theorem is the so-called first global constraint. So this tells you something about, again, these phase jumps. But now we're going to look at the sum of these phase jumps on the rotation axis. And this global constraint tells you if you sum these phase jumps up, you don't get 0, but you actually get this value here, which has something to do with the shift of the screw rotation symmetry, right? So these Weyl points, or in general, these crossings can be protected by a rotation symmetry, and this rotation symmetry can actually have a translation part. So then we call this a screw rotation symmetry. And if this is the case, this theorem tells you that the number of these phase jumps, if you sum them up, so the sum of these phase jumps has to be equal to the shift of the screw rotation symmetry. And finally, we have a second global constraint, and this has something to do with the fermion doubling theorem. So basically, this tells you if you sum up the Chern numbers of all crossings in the Brillouin zone, you must get 0. So this is because the Brillouin zone is a compact manifold, and these Weyl points can be viewed as sources or sinks of Berry flux. So whenever you have a source of Berry flux somewhere in the Brillouin zone, there must be somewhere else a region where you have a sink, such that this is consistent. Okay, so this was a little bit abstract, so let me just give you now a concrete example to see how these fundamental theorems of chiral band crossing works. And I'm going to use here this magnetic space group 19.27. So this is also called P21 prime, 21 prime, 21. So this notation means basically we have a primitive Brillouin zones. In this case, it's an orthorhombic Brillouin zone, and the space group is generated by two magnetic screw rotations. So this prime means it's a magnetic screw rotation, and by one regular screw rotation. And so these are here shown explicitly. So we have a regular twofold screw rotation. So basically this rotates here around the y-axis. So and then you have a translation part also along the y-axis, and there's also a part which rotates the spin component of the electron. And then we have these twofold magnetic screw rotation. So this is basically similar to this screw rotation, but now it's combined with a time reversal operator. So we have a magnetic screw rotation here around the x-axis and another one around the z-axis. And we will see that these three symmetries will give rise to special band crossing features in any material that has these space group symmetries. Okay, so just let me go through this one by one. So we start with the first generated, the twofold screw rotation. That's like this on the coordinate, and it basically leaves these four axis invariants. So for simplicity, I'm only gonna focus on the ky axis here. And so on this invariant axis, you can then label the eigenstates in terms of the eigenvalues of this screw rotation symmetry. And we can find these eigenvalues by just simply squaring the screw rotation symmetry. So if you apply the symmetry twice, you will see that from this part here, you get a unit translation in the y-axis. And then you square also the spin part, the Pauli matrix. So this gives you a -1. And the unit translation operator applied on a Bloch state will give you this phase factor e to the iky. So that means the eigenvalues are then just the square root of this. So basically we get these two possible eigenvalues plus or minus I from this -1, and then we get a 1/2 from this phase factor e to the iky half. So any state on this invariant axis can be labeled in terms of these eigenvalues. Okay, so and now we can see that this type of structure will necessarily lead to a crossing on the Brillouin zone, and this is a manifestation of the first global constraint. So basically, if we think about the two-band system, where we have these eigenvalues plus or minus 1 on one side of the Brillouin zone, then we know as we go to the other side of the Brillouin zone, we basically must end up with the same states because the bands are periodic. And we must kind of, somehow connect now these two states as we go through the Brillouin zone. But the point is now that because of this phase factor, you pick up a phase. So basically, as you move here along this ky axis from ky minus pi to ky plus pi, you pick up this phase. And so that means you move counterclockwise on the complex unit circle. And because of this 1/2, you don't go for a full rotation around the complex unit circle, but only 1/2. So if you start from -1, you end up by +1. If you start from +1, you end up by -1. And so that means because of consistency and because the wave functions on the bands must be continuous in the Brillouin zone, you must connect here this state -1 with this +1 and the +1 with the -1. And this can only occur through a band crossing here in the middle. So basically, this is a manifestation of this first global constraint. So that means here, if we have these phase jumps, this must be different from 0. So in our case now for this screw rotation, two-fold screw rotation, this factor here would be 1/2. So this sum of the phase jumps must be pi. Okay, this is just basically shown here pictorially how this works. Okay, so in the simplest case, we have just one crossing, and then this phase jump must be equal to pi. Now we can combine this with the first, with this local constraint here, which relates this phase jump to the Chern number. And we find from this that this phase jump of pi must result in a Chern number plus minus 1 of this crossing on this screw rotation axis. So we find, what we have found is that any material which has the screw rotation symmetry must have an odd number of Weyl points on this axis. Okay, so let me now combine this with the other two generators that we have in this magnetic space group. So the first one, the second generator is this magnetic screw rotation. So here we have a combination of a time reversal symmetry with a screw rotation around the x-axis. So this acts in momentum space like this. So basically the rotation part changes these two signs of the momentum. And then if we apply a time reversal operator, we change all components of the momentum. So basically then it relates kx to minus kx. So it's in a sense similar to a mirror symmetry. And we have two invariant planes in the presence of this symmetry, namely the kx equals 0 and the kx equals pi plane. Now, because this is an anti-unitary symmetry, we cannot use this argument as before, where we looked at the eigenvalues, but we can use here the Kramer theorem to derive the presence of band degeneracies. So to see whether we can apply the Kramer theorems, we need to make sure that the symmetry squares to -1. So let us take the square of the symmetry. So basically, because time reversal and the screw rotation commutes, we can take the squares individually. So we get a -1 from the time reversal symmetry, because it's a time reversal of spin 1/2 particles. And then we have another -1 from the spin part of this screw rotation. And then we get here this translation operator as before, but now along the x-axis. So this basically applied to a Bloch state gives you e to the ikx. And then evaluated on the invariant planes, we get either +1 for k equals 0 or -1 for k equals pi. So that means if we are in the k equals pi plane, we have indeed the anti-unitary symmetry that squares to -1. And we can repeat Kramer's argument to derive the presence of orthogonal states on this plane. So that means all the bands must be twofold degenerate on this plane. So we have found a nodal plane. That's actually was the intention at the beginning, right? But we don't know yet anything about its topological character. Now, this argument I've just made, of course, I can repeat also for the other magnetic screw rotation symmetry around the z-axis, and there we find we have a twofold degeneracy on the kc equals pi plane. Okay, so far I have used all these three generators of the space group, and I have used the local constraint and the first global constraint to derive the presence of an odd number of Weyl points on this ky axis. But what is missing is the third theorem, namely the fermion doubling theorem, which tells you that the Chern numbers summed up of all crossings in the Brillouin zone must be 0. So let's see how we can use this argument. So basically, this sum, we can split this up into different contributions in the Brillouin zone. So the first contribution is this line ky, where we know we must have an odd number. The Chern number must be odd. We must have an odd number of crossings, and their Chern numbers must add up to an odd number. Okay, so an odd number is different from 0. So that means some of these other contributions must be non-zero. So let's see how we can satisfy the fermion doubling theorem. So we could have, in principle, Weyl points at generic positions, shown here in blue. But if this happens, we can apply this magnetic screw rotation symmetry, which acts like a mirror symmetry, to generate 3 other copies. So for each generic Weyl point, there will be 3 copies, which have exactly the same Chern numbers. You can show that. And that means this contribution is an even number. So now we have an even number plus odd number. It's again different from 0. So there must be something else. So let's see if we put a whale point on one of these planes, which are left invariant by the screw rotation. So if we have a whale point here, then we have always the other screw rotation that we can apply, so we can generate another partner, which has again the same number. That means now we still have an even number plus odd number, different from 0. So how is this resolved? Probably you guessed it already. It is because the nodal plane must have a topological charge. So having used these 3 theorems, we have found that in this magnetic space group 19.27, we always must have these nodal planes, and they must have a charge different from 0. So that somehow satisfies my first motivation. Indeed, we have found a possibility where we have a band crossing on a plane with a non-zero Chern number, namely all materials in this magnetic space group will show this. So this is the principle of symmetry enforcement. And we can now generate arbitrary tight binding models satisfying this symmetry. So we know any system with these symmetries will have that, and that's what we have done here. In the simplest case is a 4-band model, because the Wyckoff position of this magnetic space group is A, is only one Wyckoff position, which has multiplicity 4. So basically 4 sublattices. And here is shown the band structure of just a random model with these symmetries. And indeed, you find here these whale points on this axis here. And you have these nodal planes here. And we can now go and explicitly compute the Chern number. And indeed, we find here Chern number +1 for these whale points, and we have Chern number -1 for the nodal plane. So how it is actually computed, this Chern number of the nodal plane? Basically, you do this by integrating the Berry curvature along a surface, and the surface is basically this red cylinder which encloses this nodal plane from the inside. Well, it's actually 2 nodal planes, one here and one here, and this remember that the Brillouin zone is actually 3 torus. So this integration surface encloses these 2 nodal planes from the inside, so to speak. Now, what's interesting is that if you look at the Berry curvature as you go perpendicular to this nodal plane, is that they show cusp and jump singularities. So this is different from a whale point where you have a divergence. And we have in particular for the component which is perpendicular to the nodal plane, we have this jump. And if you integrate up this jump, this gives you a quantized value. This will be this Chern number here. Now, if you break this symmetry, then these singularities, these kind of removable singularities, turn into real singularities. So then you get these divergences in the 3 components of the Berry curvature. So this is maybe something that one could use for an application, because we now have a handle, by breaking one of these screw rotation symmetries, for example, by applying a magnetic field, we can turn this kind of finite response into a divergent response. So this Berry curvature controls many response functions, for example, the circular photogalvanic effect. And we are currently looking at ways to measure this in an experiment. Now, there's also bulk boundary correspondence. So as I said in the beginning, these topological materials always have certain surface states. So this has to do with the bulk boundary correspondence, which is mathematically related to index theorems. So basically, this relates this quantized Chern number to the occurrence of a surface state. In this case, the surface state takes the form of an arc, which connects here the projection of the single point here to the projection of this nodal plane at the boundary of the Brillouin zone. Okay, so we can use this argument now and generalize them to general magnetic space groups. And so the basic ingredients we must have are magnetic screw rotations. So the space group must have these magnetic screw rotations. We must have a reciprocal lattice vector which relates pi to minus pi. So for example, in the primitive Brillouin zone, that's always the case. But if you have maybe a body-centered or a face-centered Brillouin zone, that can be absent in some cases. And finally, we must make sure that we don't have this PT symmetry, the inversion with time reversal, because this would lead to twofold degeneracy everywhere in the Brillouin zone. Okay, and then with these three criterion, we find that from this 1,651 magnetic space groups, basically 254 satisfy this criterion. Now, if you want that these nodal planes are also topological, then you must make sure that the space group is chiral, so there should be no mirror or inversion symmetry, because these symmetries force the Chern number to be 0. And you must also have an uncompensated Weyl point at gamma or on a screw rotation axis. So these are further conditions. So then you go down from these 254 space groups to 33 space groups, which satisfy these conditions. So basically, this is shown here. So here we have these 254 magnetic space groups that have nodal planes. Those shown in blue here, they can have a topological charge, these nodal planes, and those in yellow, they must have a topological charge. Okay, so this is basically the strategy now to find a material with such a topological nodal plane. And this tells us now any material in this yellow space group must have these features. So we can now go to these databases of materials and look up what material crystallizes in these yellow space groups. And this is what we have done. And we have found three. We have actually found many more examples, but these are just three of them. And in particular, this ferromagnetic manganese silicide has this simple space group, which I've used in the example, 19.27. Okay, so then we can go and compute with density functional theory the band structure. Now, of course, this looks much more complicated than my simple model, but these basic arguments, because they are only based in symmetry, are still there. So we find in particular on this ky axis, we have these Weyl points, which all have charge 1. And on this nodal planes, we have a twofold degeneracy, which have opposite charge to these Weyl points. Now, if you look at the Fermi surface of this material, you find that the Fermi surface crosses these nodal planes. And so there we have a degeneracy in the Fermi surface, where we have a very large Berry curvature at the Fermi surface, at least on this part of the Fermi surface. So in that sense, in these materials, there's always automatically, you have at least part of this large Berry curvature is right at the Fermi level and will contribute to transport characteristics. So we can also verify this bulk boundary correspondence for this material. So also with the DFT, we have computed the surface states, and we see here Fermi arcs that come out of the projection of these Weyl points on the ky line. There's also bulk states here, so it's maybe not so clear as in the model, but you still see here some Fermi arcs that come out of the center and which kind of connect here to bulk states at the boundary of the Brillouin zone. Okay, so then we have teamed up with experimentalists from TU Munich to verify this band structure in the Haas van Alphen experiments. And so here you can also see signature of this topology. So basically in the Haas van Alphen experiment, you measure certain orbits. So the electron in a magnetic field will perform an orbit along the Fermi surface in a plane which is perpendicular to the magnetic field. And so then we can kind of look at orbits which go through these nodal planes. So for example, here we have an orbit that goes like this, and which intersects these nodal planes here on the top of the Brillouin zone cube and on this side. And so then here and here we have this topological degeneracy. And so that means you go here from one sheet to the other, so to speak. And that means because of this topological degeneracy, you find only 1 the Haas van Alphen frequency as opposed to 2 the Haas van Alphen frequency, which you would have expected if there was no such degeneracy. So basically, you know, this area here that is enclosed by this orbit corresponds to a certain frequency here. And basically, if we have this topological degeneracy, then here we enclose always the same area, and we only see 1 frequency, and this agrees with the experiment. Okay, so this summarizes basically the first part of my talk, and I just want now to explain how these topological materials in these nodal planes might overcome some of these challenges. So first, we have found a whale point and a nodal plane, which are very far apart in the Brillouin zone. Namely, one is on this ky axis or a gamma, and the other one is at the boundary of the Brillouin zone. So we have it was almost a maximum possible distance of pi. So this will give rise to a large anomalous Hall effect, for example. And also, if we have disorder, this cannot blur out this immediately. The second advantage is this part of the nodal plane is automatically at the Fermi level. This is because as soon as you have a Fermi surface that goes through the boundary of the Brillouin zone, this will have a degeneracy, and this degeneracy in the Fermi surface carries part of this large Berry curvature. Then third, we can have now a very high charge of this nodal plane. So this is not restricted by the crystal symmetries, but we can have arbitrarily high charge. And in some materials, we have found up to charge 80. So again, this is useful if you want to look at one of these topological response functions, because they scale with the charge of this of the Chern number. And finally, we can control this degeneracy in terms of symmetric breaking. So if we break this screw rotation symmetry, then these cusp and jumps in the Berry curvature turn into divergences. So you would expect from this a large change in the response. Okay, so then with this, I come to the second part, where I'm now going to talk about topological superconductors. So again, I want to find develop a new strategy to find new topological superconductors. And I'm going to focus here on the Rashba-Hubbard system. So basically, what is the challenge that one typically has when one looks at these topological superconductors? So one of the challenges is that the transition temperature is very small. So usually it's of the order of a Kelvin or maybe just millikelvins. So that means also the superconducting gap is very small, and this topological protection is only as good as the size of the gap. So meaning any perturbation that is bigger than this gap will destroy the features that you're looking for. So we want to have something with a large TC and a large gap. So the second problem is, as I've said in the beginning, that a lot of these materials have also disorder and interaction at the same time. So this is a notoriously difficult problem in condensed matter physics, right? So people usually focus only on one of the two, but they have two at the same time. That is often very challenging to deal with. And finally, oftentimes one just looks at these topological superconductors as an interface. For example, one can have a S-wave superconductor interfaced with spin-orbit coupled semi-metal, and then one gets this state only at the interface, but then it's kind of buried from the outside and not so accessible to experiments. So we want to have this topological superconductivity ideally in the bulk, such that it can be accessed more easily to make contacts and so on. Okay, so to resolve these problems, I'm going to suggest to use this functional realization group together with the real space mean field theory. So this will resolve this problem too. And then I'm also suggesting to look at Rashba-Hubbard systems close to Van Hove fillings. So because of Van Hove fillings, you have a large density of states. So this can give rise to large TCs and large gaps. And this Rashba-Hubbard system can also be realized in materials, and therefore it would exist. The superconductivity will exist in the bulk of the system, not just the interface. Okay, so let me start off with this renormalization group mean field theory combined approach. So basically, we start from a Hubbard interaction at high temperatures. Here it's on the square lattice where we have a Rashba spin-orbit coupling term that splits the spin degeneracy of the band. We start from this at a high temperature, and then we derive renormalization groups equations at each K point in the Brillouin zone. So we have a finite set of coupling constants, but we have functions of coupling constants that we have to see how they evolve. So that's why it's called functional renormalization group. And so we're going to numerically integrate out these flow equations starting from a high temperature until a certain interaction vertex diverges, or until we reach the stopping temperature T star. And then if this happens at this stopping temperature T star, we're going to formally integrate out renormalization group equations solve the inverse Bethe-Salpeter equations, and then we get real space mean field theory of this form here, where we can self-consistently compute the gap equation with these interaction parameters here, V, where V is related to the irreducible particle-particle vertex from the functionalization group in the particle-particle channel. So basically, this method takes the interactions into account at large temperature, at larger energy scales in an unbiased way. And then when we come to this stopping temperature, we can also include then at the lower energy scale disorder, because in this real space mean field theory, we can also add disorder to the problem. Okay, it's not the perfect solution. We cannot really solve interactions and disorder at the same time. But the idea is that maybe if disorder is weak, this only matters at the low energies, and therefore we hope to get some insights with this type of approach. Okay, so we want to apply this to the Rashba-Harbert materials described by this Hamiltonian. So for simplicity, I'm going to look at the square lattices, nearest and next nearest neighbor hopping. And I'm going to include a Rashba-Spinor coupling term, which splits the band degeneracy. So this type of Hamiltonian can describe a number of systems. For example, heavy atom superlattices of this form, cerium, cobalt, indium 5, terbium, cobalt, indium 5, which have been grown by Professor Matsuda-san here at Kyoto University. And so this, depending on the thickness of these different layers, you can actually tune the Rashba-Spinor coupling and also change the Fermi surface to some degree. And so this idea has recently also been applied to this heterostructure here, where you combine europium oxide with potassium tantalum dioxide. And you can also consider here different thickness of layers and thereby tuning the shape of the Fermi surface as well as the size of the Spinor coupling. Okay, so this type of Hamiltonian can also be applied to non-centrosymmetric superconductors, maybe also to van der Waals materials. So to understand the physics here, we first need to think about the Fermi surface in these types of systems. And so what's special here is this Rashba type Spinor coupling, which breaks the spin degeneracy. So this is always present if you don't have inversion symmetry, and it leads to a spin splitting of the bands. For example, if we start off on the square lattice with a hole-like Fermi surface like this, where we have Van Hove singularities here at the X point, then once we turn on the Rashba-Spinor coupling, we split the bands, and we generate one hole-like and one electron-like Fermi surface, and we also split the Van Hove points into two. So there's one moving along here, the y-axis, and the other one moving along the x-axis. Then the density of states, that means the following. So we have here a situation without Rashba-Spinor coupling with a single Van Hove singularity from this point here, which then turns into two Van Hove singularities in the presence of this Rashba-Spinor coupling. So one has a larger density of states, this is this red one, and the other one has a little bit smaller. So now in terms of filling, means we have three different regions. So we imagine now maybe in the real material we can dope the system, and we can tune the filling here from here along this axis, or maybe we can gate the system that will also allow us to change the filling. So if we do that, we have basically three regions. We have region 1, where we are to the left of the proposed Van Hove singularities, and there we have two hole-like Fermi surfaces of this shape. Now, if we increase the filling a little bit, then this Fermi surface goes through this Van Hove point here, and basically becomes an electron-like Fermi surface, but the other one stays hole-like. Finally, if we go here to the very right, we go then also the second Fermi surface goes through the second Van Hove singularity and becomes electron-like. Okay, so now we know from a lot of studies in superconductivity, so at least in this V-coupling approach, where superconductivity is driven by fluctuations, that the shape of the Fermi surface plays an important role for the type of superconductivity you expect. We expect from general principles that in these three different regions, we should get very different types of superconductivity. Okay, so to see that, let us first look at the spin fluctuation spectrum. So this is shown the spin fluctuation spectrum as computed within functional RG. So here we are still with a little bit above the ordering temperature. The system is not yet in the superconducting phase. And what is shown here is now the spin fluctuation as a function of this filling and as a function of the second neighbor hopping T prime. And in yellow here is shown the location of these Van Hove singularities. And I have indicated these three different regions. I have region 1, where I have two hole-like Fermi surfaces, region 2, I have a hole-like and electron-like, and region 3, where I have two electron-like Fermi surfaces. And in color is shown here now the magnitude of the transversal and longitudinal susceptibility at 0. That corresponds to ferromagnetic fluctuations normalized by the maximum of these susceptibilities in the for any Q. And we find, interestingly enough, now quite different features in these three regions. So in the first regions, we have antiferromagnetic fluctuations. So they are dominate or arise usually because of nesting features in the Fermi surface. In region 2, we have ferromagnetic fluctuations, and also in region 3, we have, at least for large T prime, ferromagnetic fluctuations, whereas a smaller T prime, we have more antiferromagnetic fluctuations coming from the nesting of the Fermi surfaces, right? So this yellow here indicates this region of ferromagnetic fluctuations. Okay, so we can actually understand this at least at a simple level by looking at the bubble diagrams that enter in the spin fluctuation. In the bubble diagrams, you have the bare susceptibility entering, and they can be split up into an interband and into an intraband part in this way. And so we have here these Fermi functions, and here we have basically the spin-orbit coupling entering. So this G vector here parameterizes the spin-orbit coupling. Now, if we look at antiferromagnetic fluctuations, so that means this chi should be peaked at a P or around P, so P plus delta. Then we can expand this factor from the spin-orbit coupling, and we find that it's to leading order -1, whereas for ferromagnetic fluctuations, this term should be to leading order +1. So combining this here, we can conclude that the ferromagnetic fluctuations originate from the interband part, whereas the antiferromagnetic fluctuations originates from the intraband part. So that's why it's important to look at these Rashba systems, because we need to split up the bands. We need to split up the spin-orbit coupling such that we can get these interband effects, right? So that was the reason actually why we looked at this Rashba system. Now we can further simplify this interband effect part of the susceptibility, and then it takes this form here. Basically, you have here again one factor that comes from the spin-orbit coupling vector. So this bracket here basically diverges close to the value 0, pi 0, 0, pi, 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 because this is an antisymmetric function, meaning this needs to be 0 at this time of invariant momenta. And so that means we would expect a very large ferromagnetic fluctuations that comes from these 4 points in the Brillouin zone. But now we have to remember there's also this Fermi factor here, and they can actually be 0. And it turns out that this Fermi factor is here 0 exactly in region 1 and 3, but it's non-zero in region 2, because here you have one filled band and one empty band. So basically, you get here 0 minus 1 or 1 minus 0 or something like that. Whereas here, you have always at these 4 points, 2 filled or 2 empty bands. So basically then these two Fermi functions cancel each other. So this is a rough explanation why we can have these ferromagnetic fluctuations only in region 2. Okay, now we go lower in temperature. So we go to the stopping temperature, and then we map these renormalization group equations to the mean field equations, and we can solve them to get the gap function. And we can look at this gap function to find the different topological superconducting phases that we have. And we find basically 3 phases here, B, A1, and B2, which I'm going to explain now in the following. And here is shown the triplet to singlet ratio in these 3 phases. So basically, you know, in a superconductor, you have a Cooper pair, so 2 electrons pair up, and they can pair up in 2 different ways. So they can form a spin 0 state, so this will be singlet pairing, or they could form a spin triplet state, where you pair up, and down. And this triplet pairing is interesting because this automatically leads to a topological feature. So we see already here, we just look at the singlet to triplet ratio, that in this region 2, we can expect a topological superconducting phase. So if we actually compare this to the ferromagnetic fluctuations here, we see a nice correspondence. Whenever we have these ferromagnetic fluctuations, where you know, the spin, where we have kind of only spin up, this naturally leads also in the Cooper pairing to a pairing state where you pair up spin up with spin up electron. Okay, so let me go through these 3 different phases. Basically, region 1, we have this P1 pairing. So this takes this form. So this is the form factor of this pairing symmetry. So basically here we have a singlet part which has a D-wave form factor, cos kx minus cos ky, and we have a triplet part which has like a P-wave form factor, sin ky, sin kx. But the singlet one is here dominant, so it's like a D-wave like superconductor. The D-wave superconductor has nodes because you know, there's certain lines in the Brillouin zone where this term vanishes, and this intersects with the Fermi surfaces, then this gives rise to nodes. And these nodes, they carry a winding number similar to this Chern number that I have talked about in the beginning. And by the bulk boundary correspondence, this nodal feature of the superconductor gives rise to so-called Majorana flat bands. And this leads to a large density of states at the edge. And so basically now, yeah, so then if we kind of analyze this in this real space mean field theory, we can introduce explicitly an edge, and we find that these Majorana flat bands are unstable in the presence of residual interactions. So this is basically because we have here extensive degeneracy of edge states, which must be thermodynamically unstable, and how this degeneracy is lifted is through the formation of a phase crystal, where the superconducting phase changes along the edge of your system. Okay, then in region 2, or region 3 rather, region 2 and 3, we have this A1 phase. So this is a P-wave-like state. So again, the form factors here of this type. We have a kind of extended S-wave, and then we have kind of a P-wave-like form factor for the triplet state. And so this again has a topological character, which is characterized by a C2 number. And this topology gives rise to edge states. This can be seen here in terms of these wave function amplitudes. And if we look at the edge density of states, we have here a full gap, and then we have like 2 states which cross this gap, which have opposite spin. This is called the helical Majorana state. Now, if we are close to this boundary between region 1 and region, between this phase A1 and B1, we can have the possibility of a combined coexistence phase where these 2 order parameters combine to make a compromise. And there we have this A1 plus IB1 superconductor, where we find from the free energy that the ideal or the minimum energy configuration is when you have this phase here between these 2 order parameters is exactly I. Right, so, and then this has also interesting topology. It has a second order topology with Majorana corner states. Okay, then now to show that this approach also works in the presence of disorder, we have included on-site disorder with box distribution. And so here you see that these order parameters are stable up to rather large values of disorder. So we expect that these phases should survive even in real systems with disorder. Okay, so then I'm just briefly concluding the second part. So basically I've introduced this functional normalization plus mean field theory treatment, which can, at least at some level, solve the problem of disorder and interactions at the same time. Then I have discussed this Rashba-Haber model, and we have seen that close to this Van Hove singularity of very large TC. So this is actually shown on this slide. So here's the leading superconducting eigenvalue, and we see we get very large values here, precisely at this Van Hove singularity. So we expect that we can get TCs maybe up to tens of kelvins, such systems. And yeah, finally, this can, in principle, at least occur also in intrinsic materials, in non-centrosymmetric superconductors. So then this would occur in the entire volume. Okay, thanks for your attention. And this is my conclusion.
Thank you very much. And questions?
Yeah, it's you know, it's so oftentimes, you know, if you have like irreducible representations with two components, you can take each of these components and combine them with an arbitrary phase. So now here, these are not A1 and B1 are not the two members of a two-dimensional irrep, but you know, so that's why this can only occur at this phase boundary, right? So you need to be here at this phase boundary where both order parameters have a similar magnitude, and then you can combine them with an arbitrary phase. This is also a solution of your mean field equation, and the phase is then determined from the free energy. So to show that this phase leads to a lower value. Yeah, we find it. Yeah, it's kind of a small region here. Yeah.
Other question, comment? So I have a question about your phase crystal for the deep superconductor, and so that kind of phase crystal can appear in even in the high TCQ breaks. So I don't know that. If your argument is correct, so that should be appeared even in the high TCQ break, but I don't know that kind of experiment data. So
yeah, you're right. So basically, in the high temperature superconductors, you have a very similar pairing symmetry, but you only have the singular part. The triplet part does not exist. But the phase crystal will nevertheless appear. Yeah, I'm not. Yeah, experimentally has not been observed so far. I think the problem is in the high TC cuprates is that you are close to a antiferromagnetically ordered state, so you have basically also strong magnetic interactions. And so how this degeneracy, this large degeneracy from these Majorana flat bands is lifted is probably more through a magnetic instability. Cuprates, yeah.
Other question, comment? So if not, let's start speak again.